Okay, now, yes, thank you. It's my great pleasure, as I said, to introduce my friend Eduardo Guendelman. Apparently he's in Chile, but in a kind of virtual state in some hotel due to coronavirus. Well, Eduardo, I met Eduardo many years ago when we attended the lectures by Professor Patricio Cordero, who unfortunately passed away a couple of months ago, on quantum field theory, and other courses we took simultaneously. Then Eduardo did his undergraduate thesis with Patricio Cordero, and this work was extremely successful because this work ended with a Physical Review Letters article. After that, Eduardo went to MIT, where he did his PhD, and his advisor was Alan Guth. You know, Alan Guth created the concept of inflation in cosmology. And after that, Eduardo went for a first period to Beersheba, to Ben Gurion University in Beersheba, returning for a period of 2 years to Los Alamos in the US. And finally, he returned to Israel. Well, Eduardo was born in Chile. He's a Chilean guy, yeah? And since 1991, he is professor of physics at the Ben Gurion University in Beersheba. This is a city in the south of Israel, just where the Negev desert starts. Eduardo is a well-known world expert on questions on cosmology, inflation, false vacuum, quintessentia, etc. And we are very happy to have you with us, Eduardo. So I think Francisca should give you the authorization to start with the seminar. So welcome.
Yes, thanks, Eduardo. Please go ahead and start your talk.
Okay, it's a pleasure to talk to you again, now from a distance. I have been in person with you before. Okay, so I'm going to talk about the notion of dynamical tension in string theory and what this can do in cosmology or thermodynamics, and for the construction of new type of Braneworlds. Okay, so the idea is to explore, is more general than the application, the particular application we are considering for string theory is we consider a possibility of changing the measure of integration. The measure of integration, we can put a totally antisymmetric tensor contracted with this, right? Like a totally antisymmetric tensor in d dimension is like that. And this becomes a density that's transformed like Jacobian of Fourier transformation, and ddx transformed like the Jacobian. And yeah, so in a standard generally covariant theory, we use ddx square root of minus g and a Lagrangian scalar, right? This is the square root of minus g, where g is the determinant of the metric, is the standard canonical form. So in this case, the omega that I wrote before is the square root of the determinant. So these ideas have been used in gravity before, and I think I have given you talks on this application of gravity of these modified measures, right? And one particular way of realizing these metric independent measures, right? There's a density that is not defined in terms of the measure, like the square root of minus g. You consider, for example, 4 scalars, a equals 1, 2, 3, and contract all the derivatives, right? 4 derivatives that you can do with the epsilon mu nu alpha beta. This is in 4 dimensions, right? And you can do, you put more indices, and you can do it in 2 dimensions, which is relevant to the string, or in high dimensions, whatever you want, right? So this phi is this ABC are internal indices, right? Or classify the scalar. This is there is an invariant volume element phi ddx. Phi is a density that transforms according to the inverse of Jacobian, and ddx, of course, transforms according to Jacobian. This is the definition of Jacobian. Generic modified gravity actions involve this Riemannian volume element, non-Riemannian volume elements have been studied and were the subjects of a few talks I gave before here. And we construct the density multiplied by square root of minus, by these densities, the curvature, some Lagrangians, additional Lagrangians multiplied by another densities, and we can add also square root of minus g to another Lagrange. So this I talked before. The structure of these equations, if we vary the fields that define the measure, is like a sum derivatives acting on a Lagrangian equals 0, right? Something like this. So you get some Lagrangians equals to some constants. Okay, this is very generic. Now let's go to the application to string theory. Right? So string theory is normally defined in terms of this Polyakov action. Actually, it's called Polyakov action, but there were some people before. But Polyakov is called Polyakov action because Polyakov used it successfully to quantize. And you integrate over the coordinates of the worksheet. You define an internal metric gamma AB. You define square root of minus gamma. Gamma is the determinant of the metric, right? Defined here. G mu nu is the embedding metric, right? There is a 26-dimensional space-time, whatever. Yeah. T is a factor in front is the tension, and it's not dynamical in the standard formulation. It's a constant here, and it's the dimension full scale. So if we vary with respect to gamma, we get usually the variation in general relativity. The variation with respect to gamma is of some Lagrangian is called the energy momentum tensor. So here there is not a curvature term, so this additional term. So the curvature terms, the energy momentum tensor is equal to 0. And then there is the analogous of geodesic equation when we vary with respect to x mu. The connections appear here. Okay, but there is we want now to modify these measures square root of minus gamma. And we'll see that this gives a dynamical tension. And so the measure, as we saw in general, we contracted with the number of derivatives in 4-dimensional. There were 4 derivatives of scalar field, of 4 scalar fields. Here we use 2 derivatives of 2 scalar fields, epsilon AB, dA, dB, and then phi I, phi j is the I and j specify the number of the scalar field, just 2 scalar fields. Okay, the modified string theory action that is consistent. For consistency, you have to add the internal gauge fields. Otherwise, you get singular solutions. This fixes everything, and it's very important. It's epsilon AB, FAB. FAB is an internal gauge field strength, right? Defined the same as electromagnetic field strength, but it lives on the string. Okay, and then otherwise you use this and this, right? So this has the conformal invariance. Gamma AB goes to some J, gamma AB. the internal scalar fields undergo an internal diffeomorphism such that this J that appears here is the same as the J that appears here. This gives you conformal invariance. The equation of motion of the fields phi I gives you that there is an operator here times the derivative of the Lagrangian equals 0. And as we said, this is the general structure of this type of series, says that the Lagrangian is equal to a constant. The equation with respect to gamma are now this equals 0. You can, for example, solve the epsilon CD f CD divided by square root of minus gamma, put into here. And you find the consistency by taking the trace and comparing again with this equation. You can see that this is only consistent if m equals 0. The constant of integration equals 0. The interesting thing is the variation with respect to the internal gauge fields. It tells us that phi divided square root of minus gamma is the derivative of this is a constant. So it gives you the phi divided by square root of minus gamma is a constant. This is interpreted as the string tension. Now the string tension is derived as a constant of integration, appears dynamically, is not put in by hand. Okay, similar thing can be defined for branes. I don't go through all the story is very similar story, but just for reasons of time, I don't go through the story, but you can see in the papers that written. But this is the same thing, that the string tension, the tension of the brane is an integration constant. Now, what is different? One could say, okay, you got the integration constant, the string and the brane tensions as an integration constant. Okay, so what? What happens here is that the string generation takes place for a given worksheet. So a worksheet, a given string or brane can generate the string tension. Another string or brane can generate another string tension. So it's not universal, right? It's like similar to the multi-universe, that is in each multi-universe you generate a different cosmological constant and stuff like that. But all these strings live in the same universe, so it's not the same, but it's similar, right? Okay, so that's the Townsend had also a way to generate dynamically generate a string, but he didn't emphasize the fact that you can have different string tensions for each string. It has some gauge fields that flow around the string, and this flux can be arbitrary, giving it the arbitrary tension. It's a little bit different. Okay. Now we look at the equations of motion, and the string theory works usually like this. You put background fields, and the background fields, and then you quantize the theory in the presence of these background fields, and then you demand a conformal invariance. And miraculously, the background fields, who were just external fields, they are constrained by equations of motion. For example, the metric is constrained by, it has to satisfy the Einstein equation. And if you have a dilaton field, the source of this Einstein equation are the dilaton fields, and the dilaton fields, which is a background metric, also gets an equation of motion. This is very similar to the philosophy of Schwinger. that he has this source theory, that you can understand a theory by putting external sources, right? And as we will see in the dynamical string theory, you can add additional external fields, which are called the tension fields. And it also gets dynamics, right? Okay. How we generalize this theory so that we get a more dynamical string tension, because we got dynamical in a sense, but we just get a constant. It's not too dynamic. It's very simple. You add the interaction of these internal gauge fields that live in the brain for the string p equals 1, right? And then the equation of motion with respect to the internal gauge fields gets modified. Now the derivative of the tension phi divided by square root of minus g is not a constant, is the current that I have. Now I want to define this current from an external field, a scalar field. Suppose that there is a scalar field defined in the bulk, and this field in the bulk induces a current, a conserved current in the worldsheet by projecting the derivative of the scalar field into the Brane, into the string, right? And then you have a E, some constant, a dA phi epsilon AB. And this respects gauge invariance in the string of these gauge fields. Okay. And then you can integrate. For each string, you integrate, all right? And there is a constant of integration, Ti. So the string tension now is phi divided by square root of minus gamma equals E phi plus Ti. So from here, you can solve the measure actually in terms of the square root of minus gamma times a factor. So each strings can be quantized separately. This, I have just realized that this is can be justified very well, because this Ti actually corresponds to some conserved quantity. There is a symmetry that gives you this a conserved quantity, which is exactly Netter symmetry, which is exactly Ti, which is the shift of the gauge fields internally by a constant. This gives you a conserved quantity. Now there is the different sectors of the theory that are characterized by a different conservation law for different current. They cannot mix. This is a so-called a super selection rule. So you can quantize each sector of theory with the different concept of integration Ti separately. Okay. Now, what happened now? Now we, in the action that we wrote before, we replaced the measure by, this is the action of a string number I. The measure was the measure phi. Now we solve the measure phi in terms of E phi Ti times square root of minus gamma and all that. So it looks like the same action as the string theory, regular string theory, just that you redefine the measure by a conformal factor, right? You multiply this by this, yeah. And now you can apply, each string has a, right? Suppose that we have a, yeah, and then the condition of conformal invariance works fine for d equals 6, right? For each type of string, right? If all the constants of integration are equal, this scalar field cannot be determined because there is like a global, a local conformal invariance. You can redefine the measure because you can reabsorb all this scalar field, this tension field into the the metric by a conformal transformation of the metric. But now, if there are different types of string, you cannot do this because this conformal transformation will have to be different for each string. Right? So what do we do now? We consider two types of strings. With the it's not that there are two strings. There are two types of string. Each string has a different constant of integration, and they are different, right? And there are two string metrics, J mu nu 1, this is by this conformal factor times G mu nu, and G2 mu nu times this, and a different conformal factor and G mu nu. As we are being taught by the string theories, now I take a simplification that the dilaton field, the two index antisymmetric tensor, I take them as trivial to simplify the application that I want to do. Right? So in this case, the string theories tell you that both the metric 1 and the metric 2 have to satisfy the vacuum Einstein equation. But this is very non-trivial because the vacuum Einstein equations are not conformal invariants. So this means that there is a non-trivial condition for the tension field phi. Right? Okay. Suppose that they are related by this conformal invariant. There is a factor C here, right? Something like this. So from this equation and the same, from here I can solve the scalar field phi, and then I put back into the definition of the tension of the first string and the tension of the second string, and I get this, right? And this factor C here is physical because I could, for example, even if it's a constant, it's physical because I could, for example, if it's flat space or something, I could rescale it. But I have two metrics, so I cannot rescale it in both metrics, right? So I can define the square root of G1 divided by square root of G2, which is a scalar, and this is a power of C. So that is scalar. So there are many situations where multiply a solution of Einstein equation by constant gives another solution, like Schwarzschild solution, Kastner solution. Right? Okay. But I want to do something a little bit less trivial. I want to consider, for example, flat space. In the Milnor representation, it's right, there is a representation of the flat space, and d equals 4. It's like, it looks like a cosmology with the k equals -1. But this you can generalize for any spatial dimension, right? So you can put d-2, a sphere of d-2, sinus hyperbolic of chi, right? And you can take d equals 26. Now I want to consider this metric as, say, G1, and the metric that is obtained from t goes to 1 over t from this, and then multiplied by a constant, which obviously satisfies also the vacuum Einstein equation, because the first one is just flat space and the other one is just flat space. We just did a inversion, Fourier transformation. Right? But I said the two together cannot be eliminated by, this one can be put in terms as a Minkowski space. But I have another flat space that then I cannot put it. So it's a way to get the curvature from two flat space in a sense. Curvature to me meaning that the situation is not two flat spaces, trivial flat spaces. Okay, so there are two non-trivial metrics, and then I can apply the formalism from the conformal transformation of the metric. from the equation before, I can obtain the string tensions. And so the string tensions, and then I can obtain the solution for the metric G mono. There is the metric G mono 1, there is the G mono 2, and then there is the original metric. I can solve for that, right? There is a conformal transformation here. And if the conformal transformation is negative, right? So the conformal transformation is sigma divided by t to the fourth, because minus k where k is positive, this represents a bouncing universe, or something like that. Non-singular, this universe. Okay. And the metrics are the scalar fields, the tensions are in the early universe, you have negative tensions, a constant negative tension, they go to 0. And then in the late universe, you get constant positive tensions, and the negative tensions go to 0. Okay, this is a way, this is one kind of solution. Another solution is the wrapped space-time. There is a coordinate that's L squared is a common factor of all the other coordinates, right? Something like this. And then we have dl squared. This space-time was discussed by Wesson, for example. And then it can be, if I look at the L equals constant, this defines, this subspace defines the de Sitter space. Okay. Now we can do the trick that we did before by considering L goes to 1 over L instead of T going to 1 over T. I just another example of this type of metric where we put the Schwarzschild de Sitter, give you in a different kind of coordinates. So you can generalize this type of space-times by put L squared G bar, where G bar is D minus 1, the Schwarzschild de Sitter, for example. And this is a solution of vacuum Einstein equations in d dimensions. Okay. And then I consider another metric by considering L going into 1 over L, and then multiplying by a constant. And then again, I consider the solution for the metric, which has the geometry of a wormhole, something like this. It's non-singular. And again, there is a region in space that there is a wormhole. There is a regional space where the tensions are positive, the regional space where tensions are negative. Okay, that's a solution, right? Now I want to forbid the one nice thing is there in the previous solution is that you avoid the singularities, because it's known that by violating energy conditions you could violate singularities, and apparently it works similar here. Now I want to consider positive tensions. The two tensions are equal, and then at the end of the talk I will consider Braneworlds. Okay. Maybe the most shocking application is the Brane. Okay, but I'll go, but it's not the simpler one. So I'm going to this, the same type of metrics that we studied before, cosmological metric, which is flat space. We do the T goes into 1 over T. If we use Minkowski coordinate, this corresponds to the famous inversion transformation. X mu goes to X mu divided by X squared. If we multiply by, we prefer to do in these coordinates, in the Milne coordinates. Now we multiply by constant, which is positive after the conformal transformation. So the conformal factor is this guy. The conformal factor, according to the equation that we had before, defines the tension of of the strings. When we have the conformal factor, the conformal factor, now I call it omega squared because the conformal factor is positive. So now we have a equation for the tension field is like this. E phi plus T1 equals omega squared times E phi plus T2, which allows me to solve for the tension field E phi omega squared T2 minus T1, 1 minus omega squared. And then this, I go back to the tensions of the individual strings. If E phi T1 is the tension of the string 1, E phi T2 is the tension of the string. And I take this constant T2, constant of integration, such that T2 minus T1 is a constant. Omega squared is also positive. As because of that, we gave it the name of the conformal factor omega squared. Right? Okay. Now we look at the metric G mu nu, not the metric G mu nu 1, G mu nu 2, the metric G mu nu. And then there is a time where there is a singularity. And yeah, and then this time we call it T star, right? This is defined in this way. And okay, at this time, at this point at this point, singular point of the universal metric, the omega square goes to 1. And then from the expression of the string 1 and string 2, you can see that the string tensions of both strings is positive and infinite, goes to infinity. So we were taught that in the string theory, there is a maximum limiting temperature, right? Which is the so-called Hagedorn temperature, which is proportional to the string tension. A string tension is infinite. So this suggests that the string tension, there is no, at these points, the string tension, the Hagedorn temperature does not exist because if its Hagedorn temperature is infinite, that means that there is no constraint on the maximum temperature, right? Okay, this is a suggestion. The explicit calculation is very hard, but so far this is a suggestion that this should happen. Because, okay, the same thing one can do with the warp, Wesson warp spacetimes. The Wesson warp spacetimes is this, right? Then we do or generalize like a Schwarzschild de Sitter. We generalize to d dimensions. We again do the L going to 1 over L and multiply by constant and get the additional, we get the conformal factor here. Right? Okay, and then what we do is, well, we can again study the physical metric, the universal metric, the metric G mu nu instead of G mu nu 1, G mu nu 2. Okay, and there is the factor that multiplies L square, or here explodes, right? So there is a singularity. But there is also the tension of the strings as we approach this point, the tension of the strings goes to infinity. So there is a surface, right? L equals L star, where the tension of the strings is infinite. Okay. So if you raise the temperature, all kind of regions will have a Hagedorn temperature, which is not infinite, but apparently the strings would like to condensate in the region L equals L star, because they are, if we are above the temperature a certain temperature, everything would like to go into that surface, right? Okay. Now I do what I consider perhaps the most shocking application is the construction of Braneworlds. Now we consider two flat space Minkowski two flat space-time. One, I take Minkowski coordinates, and the other, I take Minkowski coordinates after spatial conformal transformation. The inspector, I have to take care of the inspector.
Don't worry, Eduardo. It's fine. Ivania, can you pause the video in the meantime, please?
No.
Hey, Eduardo, thanks.
Yeah, I just reported to the inspector. Otherwise I go to jail. Okay. So, okay, so now what we want to do is application that gives us finally Braneworlds. And we use two metrics. They both will be flat, but one is flat in Minkowski space, and the other is Minkowski space after a special conformal transformation. So the transformation is x mu psi prime equals x mu plus a mu x squared divided by this denominator. Okay, and a mu is a in 4 dimensions would be a 4 vector. In d dimension it would be a d vector, right? And the conformal transformation. So G1 we can take it as a eta AB, right? When eta is the Minkowski, and G2 will be omega square eta AB, which is equal to this notation is not very good because we're using 5 for something else. So forget about that. This is the conformal factor. It's something square, right? This something. And now we look at the tensions with this, the equation for the tensions with this omega square, given like that. So we can consider two different cases. A square equals 0, which is light HA, and a square not equal to 0, which can be space-like or can be light-like. Okay? A square equals a mu, right? And x square is x mu, right? These are contracted with eta mu, right? Okay, so omega square equals this. Now let's take a mu equals parentheses a 0, 0, 0, 0. So this is a time-like a. In this case, the conformal factor is 1 over parentheses 1 plus 2 a mu x mu square equals to this, right? And then I can calculate the string tensions for the string 1 and string tension for the string 2. There is this factor T2 minus T1, and the numerator is positive, and the denominator is the same in the two cases. So now there is a region of T minus x that allows for tensions to be positive, and at the boundary of these regions, right? So one of the boundaries is minus 1 over a, and the other boundary is a 0, right? At the boundaries of this space-time, you see that the boundaries are this diverges or this diverges, right? At these boundaries, the string tensions go to infinity. So you would say, and then this is a boundary for t minus x. So in a space-time, this brane, so to speak, moves with the speed of light. And we call it the brane because the idea of a brane world is that the matter is confined to a certain small region of space, right? Something like that. And this is dynamically generated because the string tensions become infinite. So, like if you have a particle whose mass becomes infinite, it's like a bug model, right? That you cannot escape or something. Okay. So this is the particular case that this A mu is light, and then we get this light-like brane world, something like. Now we can get a little bit more normal type of brane worlds if we take A mu, not light-like. We take it A mu square, A square, different from 0. Okay. And then we will have a thick brane worlds, right? And we will see what are these brane worlds doing. We calculate again the string tensions of the string 1. We get a very similar situation. A factor numerator for here this case, which is positive, and this factor T2 minus T1. And here is a, you see this factorizes, right, into 2 factors, right? And we take, for example, we are interested in the regions, the surfaces, really, the surfaces where this thing diverges, right? The string tension will diverge where this equals 0 and or where this equals 0, right? Both strings have the same divergence because the denominator is the same, right? And we want to see how these surfaces look like. For example, take A mu time-like. So A mu equals A 0, 0, 0, 0, right? So what do we get here? The first surface gives us, then I calculate this, right? The first surface implies a surface like this, right? And then another surface is like this, right? So you see this is like a hyperbola, right? Hyperbola, that this is an hyperbola centered with the natural time t equals minus a. We can redefine time, and this looks like a hyperbola, right? Something like this. And this other surface is inside this bouncing, right? Bouncing bubble. This is like a bubble that is bouncing, right? Doesn't get to 0. This is a bounce. This is a surface that doesn't exist everywhere. This one exists everywhere, but this one appears at certain times, and it becomes always inside this other one, right? Appears, and then it comes from infinity. It disappears, and then after sometimes it appears again, right? Okay, this is explained where this internal one collapses at 0 radius at some times, and then it appears from t equals 0 at some other time. And the other one is, so there is between these two surfaces, we have the situation again that the tension at the surface is infinite, and for very, very large times, these two surfaces have a very, very smaller and smaller distance between them. So this is a really realization of a thin world, because a Braneworld, because the idea of the Braneworld is that you concentrate all matter, and here is not all the matter because it's all the strings. Doesn't matter if it's open strings or closed strings, all the strings are being concentrated here, right? In the regular Braneworld, the open strings can escape the brain a little bit. Here is not, right? The situation with the space-like A mu is very similar, just that the surfaces get, we take A mu equals parentheses 0, A 0, 0. Yes. Okay, so we have we take now A mu 0, A 0, 0, 0. Before we took A 0, 0, 0, right? The situation is like, right, now the x1 gets shifted in a sense. The center of the bubble is not at x equals 0, is at x1 equals 1 over A. And the two bubbles are like this. One is like that, and the other is like that. This bubble is outside. It's encompasses. This bubble is inside this other bubble, right? So it's the same thing. So it's basically there is no new effect considered time-like or space-like, right? A mu. So again, at these surfaces that whose distance, the distance between them becomes very, very small, we have that the tensions at the boundary, tension inside between the boundary, the tensions are positive, and at the boundaries the tension becomes infinity, and this gives us a Braneworld scenario where all matter and gravity is confined between the boundary, and the distance between the boundaries as the times evolves becomes very, very, very small. Okay, and considering all this, we have, yeah. So I'm almost like at the end of the talk. Just give you a little bibliography. You just have to go to the last paper on this, which is going to appear. I just sent the proofs today in the morning. So it should appear very soon. You can get it from European Journal C, the European Physical Journal C, or you can look at the archives. And all the rest, all the other published papers or the ones that are not published yet, they are all contained in the references here. Okay, thank you very much. And that's
Many thanks, Eduardo, for the very nice talk. Is there any questions from the public?
I have a question.
yes.
Hi, Eduardo.
Hola.
Hola, hola. You know that these world spring models have a critical dimension, and that dimension depends on the field content. So, for example, for the bosonic spring is 26, for the fermionic one is 10. So, if you're adding extra fields to the world sheet model, I would expect a change in the critical dimension. Can you elaborate on that?
No, we are not adding because this. Let's see. This tension field is no. We are not adding coordinates or anything like that. These are external fields only, and the external so we are not adding additional fields.
Let me ask you the question in a different way.
And what happened is the quantization involves the quantization involves the metric G-mono1 or G-mono2 is done separately for the two strings. So because there is a super selection rule, because the tension, the constant of integration is right. So only the tension field is determined only by but it appears as a background field. It's not a field that lives in the string. If I would agree with you if I was adding fields in the string, but this is not where.
Let me ask you the same question.
Because for example, for example, 26 dimension is the fields that lives in the worksheet, right?
No, I get that, but you said that these models are conformal invariant because you are adding something that does depend on the worksheet metric. Yeah. Well, are they conformal invariant at the quantum level?
Yes. Well, this is the condition of beta function is the condition of conformal invariant at the quantum level.
And the critical dimension is.
I assume it's 26 still, right?
26. Okay. Thank you.
I could do. I don't know. One should invent the superstring analog of this, right? Everything will be.
Well, with background fields might not be easy.
Yeah.
Okay, thank you.
Thank you.
Thanks, Max. Is there any other question from the public? I think not. Okay, so let's thanks again, Eduardo, for this nice talk. Marcelo, do you have a question or not?
No, thank you. I have to digest all this.
I'm the same, yes. Okay. Eduardo, many thanks again. Have a nice
you. And I hope I will
quarantine.
be able to visit you in person during my visit to Chile. Yeah.
Great. Okay. Thank you all. Have a nice week and see you next Thursday.
Bye.
Bye.